Somewhere tonight, while you are settling into the quiet of your room, a radio telescope somewhere on Earth is also listening. Not for anything in particular, just listening. It sits beneath an open sky, maybe in the high desert of New Mexico, where the air is so dry and the population so sparse that the stars look close enough to touch. Maybe in the Okanagan Valley of British Columbia, surrounded by hills and orchards that go dark and silent well before midnight. Maybe under the wide Australian sky, where the Milky Way rises so bright on clear nights that first-time visitors sometimes mistake it for clouds. No one is standing next to it. No one needs to. The telescope runs through the night on its own, patient in a way that human beings rarely manage, scanning frequencies that human ears will never hear, recording data that no single person could read in a lifetime. You are lying down. The telescope is listening, and somewhere between the two of you, in the dark above the atmosphere, something is coming. It has been travelling for a very long time. At some point tonight, maybe in the next hour, maybe right now as you are reading this, the telescope will catch it. The signal will arrive as a ripple in radio frequencies, a brief disturbance in the data stream, lasting a few milliseconds, perhaps less. Then it will be gone. No alarm will sound. No light will flash. The data will record a small spike, and the night will continue as if nothing happened. But something happened. What just touched that telescope began its journey before your grandparents were born. Before their grandparents were born, before the first human being ever looked up at a night sky and wondered what was out there, the signal that just arrived at a metal dish in a quiet field on Earth started travelling when this planet looked nothing like the place you live on now. That signal lasted a few milliseconds. Its journey lasted billions of years. There is no frame of reference in ordinary life for that kind of imbalance. Nothing in a human day prepares you for it. Tonight, while you are here and the world outside has gone quiet, that is the story we are going to follow. A signal, a journey, and the long, strange, beautiful process of a species learning to hear something it never knew was there. For most of human history, the night sky was a ceiling, a beautiful one. People looked up and saw stars, planets, the slow arc of the Milky Way on clear nights far from cities. They named constellations after animals and heroes and gods. They used the positions of stars to cross oceans, plant crops, mark the passing of seasons. Entire systems of meaning grew up around what they could see overhead. But what they could see was only a fraction of what was actually there. The human eye is a remarkable instrument. It evolved over hundreds of millions of years to do exactly what it needed to do, which was detect the kind of light that our sun produces most abundantly, the wavelengths that help a creature find food, recognize faces, spot a predator before it gets too close. Our eyes are tuned to a very narrow slice of reality. And for most of our history, we assumed that slice was the whole thing, the universe. It turns out, it does not share that assumption. The full range of electromagnetic radiation in nature stretches from radio waves longer than a football field to gamma rays smaller than an atomic nucleus. Visible light, the only part our eyes can detect, sits in a band so narrow that if you stretch the entire electromagnetic spectrum across a football field, the portion we can see would be roughly the width of one blade of grass. Everything else passes through us without our knowledge. Radio waves from distant galaxies are moving through your body right now. X-rays from exploding stars cross this room while you read the last sentence. Infrared radiation from the warm objects around you fills the air in every direction. The universe has been bathed in energy at every frequency imaginable, and for most of human history, we had no way to know any of it existed. We were living under a sky we could not hear. The first real hint of this came from a man who was not looking for cosmic mysteries at all. His name was Carl Jansky, and in 1931 he was working as an engineer for Bell Telephone Laboratories in Holmdel, New Jersey. His job was practical and unglamorous, figure out where the static on transatlantic radio calls was coming from. He built a large, rotating antenna and spent months tracking every source of interference he could identify. Thunderstorms accounted for some of it. Nearby electrical equipment accounted for more. But there was a third type of hiss that he could not explain. It was faint, almost featureless, and it came from a direction that shifted slowly over time. Jansky tracked it for months. He noticed the shift repeated on a cycle of 23 hours and 56 minutes. That is not a random number. It is the length of a sidereal day, the time it takes Earth to rotate once relative to the stars rather than the Sun. The hiss was not coming from Earth at all. It was coming from the center of the Milky Way. Nobody asked Jansky to discover that our galaxy broadcasts in radio. He was trying to clean up telephone calls. But the universe does not wait for formal invitations. It had been transmitting on frequencies we never thought to listen for. And an engineer troubleshooting static in New Jersey happened to be the first person to notice. Word of Jansky's discovery spread slowly through the scientific community, and the implications took years to fully sink in. If the Milky Way produced radio waves, what else did? If our own galaxy was broadcasting, what were other galaxies doing? The questions opened gradually, like a door swinging wide on an unexplored room. Over the decades that followed, researchers began building instruments specifically designed to detect radio signals from space. What they found astonished them. The universe was not the quiet, orderly place the visible sky suggested. Radio telescopes revealed jets of energy shooting from galactic centers. They found vast clouds of hydrogen gas drifting between the stars, humming faintly across interstellar distances. They found pulsars, the collapsed remnants of dead stars spinning hundreds of times per second. Sweeping beams of radio emission across the cosmos like lighthouses, with no ships to guide. The sky that looked silent was full of voices. Here is the thought worth sitting with before we go any further. If your eyes could see radio waves, the night sky would not look dark. The Milky Way would glow in ways our photographs have never captured. Regions that appear empty through an ordinary telescope would blaze with emission from gas clouds and magnetic fields and the scattered remnants of ancient explosions. The universe we see with our eyes is like reading the first line of a very long book and deciding you have understood the story. We had been looking at the sky for thousands of years, and we had been hearing almost none of it. That is the condition in which the story of fast radio bursts begins. Not with a dramatic announcement, not with a single breakthrough moment, but with the slow accumulation of better ears and the quiet, patient certainty that the universe had been trying to say something for a very long time before anyone on Earth learned how to listen. There is a number at the center of this story, and it is almost insultingly small. 1 millisecond, 1,000th of a second. The time it takes a hummingbird wing to complete a single beat. The time a professional photographer's shutter stays open on a fast action shot. The time your nervous system needs to begin registering that you have touched something hot, before the pain signal has even reached your brain. That is how long a fast radio burst lasts. A few milliseconds, sometimes less. And in that sliver of time, something out in the universe releases more energy in radio waves than most objects produce in years. The most powerful fast radio bursts appear to approach. In those few milliseconds, an amount of energy comparable to what our sun radiates over the course of several days. Not every burst reaches that scale. They vary widely, but the strongest ones sit at levels that make the word powerful feel inadequate. Think about what the sun produces in a single day, every hour. Our star fuses roughly 4 million tons of hydrogen into pure energy. That energy travels 93 million miles to reach us. And when it does, it drives weather systems, feeds forests, warms oceans, powers the entire web of life on this planet. A single day of solar output could power human civilization as it exists today for hundreds of thousands of years. The most powerful fast radio bursts appear to approach that, in radio wavelengths, in milliseconds, from something that may be smaller than a city, That last part is the piece that changes everything, and the reason is not immediately obvious. So stay with it for a moment. When scientists detect a signal from space, the duration of that signal tells them something fundamental about the size of whatever produced it. This is not a guess. It follows directly from the speed of light, which is the fastest that any information can travel. Picture a source of radio emission that is as wide as our entire solar system. If that source suddenly brightens, the radio waves from the near side reach us slightly before the waves from the far side. The signal does not arrive all at once. It smears out across time, stretched over, however long it takes light to cross the diameter of the source. For something the size of our solar system, that smearing can last hours. For something the size of a galaxy, the smearing can last thousands of years. A signal that lasts only a few milliseconds cannot come from something large. The math simply does not allow it. For the burst to be that brief, the region producing it has to be extraordinarily compact. Not as wide as a star, not as wide as a planet, probably no larger than a few hundred kilometers across, and possibly much smaller. This is what makes the millisecond so important. It is not just a description of how long the burst lasts. It is a clue, a physical constraint, a fingerprint pointing toward a class of objects that can only exist at the most extreme end of what the universe permits. When a physicist looks at a millisecond duration burst releasing that kind of energy, they are not just seeing something brief and powerful, they are reading a message written in physics that says, very clearly, whatever made this was small, dense, and operating under conditions that nothing in ordinary human experience comes close to. The millisecond is not the limitation of the signal. The millisecond is the first thing the signal tells us about itself. And what it tells us points somewhere specific, not towards something large and diffuse like a gas cloud, not towards something ordinary like a star going through a normal phase of its life, towards something compact, something extreme, something that stores energy in ways that strain description and releases it in moments that border on the instantaneous. We did not know what that something was in the beginning, but the millisecond was already pointing in a direction. One more thing worth noting before we move forward. Fast radio bursts are not the first time that a simple measurement of duration led astronomers somewhere unexpected. When pulsars were discovered in 1967, their rapid, precise timing told scientists immediately that the source had to be tiny and spinning incredibly fast. That constraint led directly to the realization that neutron stars, objects containing more mass than our Sun, compressed into a sphere 20 kilometers wide, were real, and not just theoretical. The universe hides its most extreme objects behind ordinary-sounding numbers. A fraction of a second, a small spike in a data stream, a few milliseconds that carry the weight of billions of years. In 2001, a signal arrived at a radio telescope in rural New South Wales, Australia. Nobody noticed. The Parkes Observatory had been one of the most respected radio telescopes on Earth since it opened in 1961. Australians called it simply the Dish. It had helped track the Apollo missions. It had contributed to decades of pulsar surveys, quasar studies, and the slow, painstaking work that built radio astronomy into a mature discipline. The people who worked there trusted the data it produced. They stored everything carefully. They came back to old archives when new questions arose. In 2001, the Dish was conducting a pulsar survey. A team was scanning sections of sky methodically, recording everything, storing it all in archives for later analysis. When the signal arrived, it registered briefly in the data stream as a bright spike across multiple frequency channels. Then it was gone. The system logged it automatically. No one was watching that particular data channel at that moment. The signal sat in an archive for 6 years. In 2007, a young astrophysicist named Duncan Lorimer and his graduate student David Narkovich were going back through that old Parkes data looking for pulsars. This is exactly as unglamorous as it sounds. Pulsar searches require this kind of work, patient hours staring at archived observations collected years earlier, looking for periodic signals that might have been missed the first time. Most of the data yields nothing new. That is the nature of the work, and most researchers accept it as part of the job. Narkovich found something that was not a pulsar. It was a single bright burst, brief, intense, and spread across frequencies in a very specific way. It did not repeat. It did not have the regular clockwork timing of a pulsar. It appeared once, blazed across the data, and disappeared completely. The kind of thing that, in another circumstance, might be dismissed as interference and moved on from, but the way the signal was spread across frequencies gave it away. It had arrived years earlier. It had been sitting inside the data like an unopened letter no one knew had been delivered, not because no one cared, but because no one knew yet that letters like this could exist. To understand why the frequency spread mattered, you need to know one thing about how radio waves behave in space. Space is not perfectly empty. Between the stars and between galaxies there is thin diffuse gas, mostly plasma, protons and electrons drifting in enormous quantities across incomprehensible distances. When radio waves travel through this plasma, different frequencies are slowed by slightly different amounts. Higher frequencies push through more easily and arrive first. Lower frequencies are held back a bit more and arrive later. The effect is small over short distances, but over billions of light years it accumulates into something very measurable. The result is that a signal which started as a simultaneous burst across all frequencies arrives stretched out, cascading from high to low, like a chord played all at once on a piano that becomes a slow descending scale by the time you hear it. The amount of that spreading tells astronomers directly how much plasma the signal travelled through, and from that, roughly how far it came. When Lorimer and Narkovich measured the spread of their signal, the number they got did not make sense for anything within our galaxy. The signal had travelled through far too much plasma to have originated anywhere near us. It had to have come from outside the Milky Way entirely, from another galaxy, from so far away that the light travel time was measured not in thousands of years but in billions. That was when the ground shifted. A radio burst from another galaxy meant something that had seemed merely curious was suddenly extraordinary. The signal was not a local glitch or a nearby anomaly. It had crossed billions of light years of intergalactic space, arrived at a radio telescope in rural Australia, and sat unnoticed in an archive for 6 years. Now, science has been embarrassed before by signals that turned out to have mundane explanations. Parkes itself became briefly famous for a mystery called the Periton. For years, researchers kept detecting strange radio bursts they could not explain. The signals were brief. They showed up consistently, and they had properties that suggested something genuinely unusual was going on. Teams spent considerable time and energy trying to figure out what was producing them. The culprit turned out to be the microwave oven in the observatory break room. Specifically, it was staff members who opened the microwave door before the timer finished, releasing a burst of radio interference that the telescope occasionally picked up during observations. Nobody is proud of this chapter in the history of Parkes, but it is an important one. Radio astronomy is hard. Interference comes from everywhere. The most responsible thing a scientist can do when they find something surprising is to spend real effort looking for every way they might be wrong before allowing themselves to believe they might be right. Lorimer and his colleagues did exactly that. It took years of additional work, checking and rechecking, before the broader scientific community accepted that the signal was real. There was no microwave oven explanation for this one. The burst was genuine. It had come from outside the galaxy, and it had been sitting in a data file since 2001, completely unrecognized, because no framework existed yet for recognizing what it was. Think about what that means. When Jansky picked up the Milky Way's radio emission in 1931, the universe revealed that it was louder than anyone knew. When Lorimer and Narkovich opened that archive file in 2007, the universe revealed something else entirely. It had been sending signals across billions of light years for longer than any living person could remember, and humanity had only just, in the span of a single human lifetime, built the ears to hear them and the patience to look for them in old data. The signal that arrived at Parkes in 2001 did not know it would change anything. It did not know it was historic. It had left its source billions of years before the concept of a radio telescope existed on Earth. It crossed distances that reduce every human achievement to a footnote, and then it arrived quietly, on an ordinary night, and went unnoticed in a data file for 6 years. The universe is not always dramatic about the things that matter most. Sometimes it leaves something in your inbox and waits to see how long it takes you to open it. Every traveller picks up traces of the road. A person who walked through a rainstorm arrives at your door with wet clothes and mud on their shoes. A letter passed through many hands over a long journey shows it in the worn edges. The faded ink, the small tears at the corners. Even light carries the memory of what it passed through. The red of a sunset is not decoration. It is evidence. The atmosphere scattered the shorter wavelengths away and left the longer red ones to reach your eyes. The colour is a record of a journey. Fast radio bursts carry a record of their journey too. That record is written in something called dispersion. And we touched on it briefly when talking about how Lorimer and Narkovich knew their signal had come from outside the Milky Way. But dispersion deserves more time, because it turns out to be one of the most important things about fast radio bursts, not just as a measuring tool, but as a window into parts of the universe that no telescope can photograph directly. Here is how it works. Radio waves come in different frequencies. The way visible light comes in different colours. When radio waves travel through the thin plasma that fills the spaces between stars and between galaxies, different frequencies interact with that plasma in slightly different ways. Higher frequencies push through relatively easily and arrive first. Lower frequencies are slowed a little more and arrive later. The effect is tiny over short distances, but when a signal has been travelling for billions of years, crossing billions of light-years of space filled with thin gas, those tiny differences accumulate into something very measurable. By the time a fast radio burst reaches Earth, the signal that started as a simultaneous burst across all frequencies has been pulled apart. The high-frequency components arrive first. The low-frequency components arrive later, sometimes a full second behind, even though every part of the signal left its source at exactly the same moment. Picture a foot race. Hundreds of runners start from the same line at the same instant. They are all moving, but over a long enough course, small differences in speed begin to matter. By the time they reach you at the finish line, they have spread out into a long procession. The first runner arrives, then a group, then more, straggling in over the following minutes. By looking at how spread out they are, you can estimate how long they have been running. Astronomers call the amount of spreading the dispersion measure. It counts, essentially, how many electrons the signal passed through on its journey. More electrons means more spreading. More spreading means a longer journey through more material. What this means in practice is something quite remarkable. A fast radio burst does not just arrive as a flash of radio energy. It arrives as a stretched cascade of frequencies. And buried inside that cascade is a record of everything the signal passed through on its way across the universe. The dispersion measure is the signal's autobiography, a log of its travels, written in physics, that any astronomer with the right equipment can read. When Lorimer and Narkovich measured the dispersion of their 2001 signal, the number they got was far larger than anything that could be explained by plasma within our own galaxy. The Milky Way has plasma in it. Naturally, all galaxies do. But there is a maximum amount of dispersion that our galaxy can contribute to any signal. Based on how much plasma we know exists along various lines of sight through the galactic disk, the signal they found exceeded that maximum by a significant margin. The extra dispersion had to come from somewhere beyond the Milky Way. The signal had travelled through intergalactic space, through the thin and largely invisible gas that drifts between galaxies, and that gas had left its fingerprints on the signal's frequencies. The burst was not just from outside our galaxy. It was from very far outside. Sit with that for a moment. We are not simply detecting a distant explosion and marvelling at how bright it was. We are reading a record. We are looking at a signal that carried evidence of its entire journey inside its own structure. and we have developed the mathematics to decode that evidence. The signal arrives and immediately tells us, here is how far I came. Here is what I passed through. Here is the physical state of the universe along the path I travelled. Think about what the signal crossed to get here. It left its source in some distant galaxy. It crossed the interior of that galaxy, picking up dispersion from the plasma between its stars. Then it entered intergalactic space and travelled for billions of years through the vast near-empty regions between galaxy clusters. It passed near other structures, maybe through the halos of galaxies it flew close to, each one adding a small contribution. It entered our local group. It crossed the outer regions of the Milky Way. It moved through our interstellar medium, and finally it arrived at a dish in Australia, stretched across frequencies in a way that recorded every environment it moved through. A signal lasting a few milliseconds at the telescope carries billions of years of history inside it. Scientists have a word for instruments that gather information about their environment as they pass through it. They call them probes. We build probes deliberately. We spend years designing them, billions of dollars launching them, teams of engineers keeping them running. The Voyager spacecraft are probes. They carry instruments measuring the solar wind, the particle density, the magnetic fields along their path through the outer solar system and beyond. Fast radio bursts are probes the universe makes for free. Nobody sent them. Nobody designed their instruments. But as they cross the cosmos writes on them. And when they arrive, if we know how to read the writing, they tell us things about the space they crossed that we have no other way of learning. We just have to be listening when they arrive. And for most of human history, we were not listening at all. Close your eyes for a moment and try to hold a number. 3 billion years. Not 3 million. Not 300 million. 3 billion years. If you counted one number every second without stopping, reaching 3 billion would take longer than recorded human history has existed. 3 billion years is a span of time so enormous that the human brain does not actually process it as a duration. It processes it as a category, something filed under very long time and left there without further examination. But some fast radio bursts have been travelling roughly that long before they reach us. And what I want to do in this chapter is not explain that number, but try to make you feel it, even imperfectly, because feeling it changes something about what it means when a telescope catches one of these signals. When a particular fast radio burst left its source in a distant galaxy, our planet already existed, but it looked nothing like the world, you know. For a burst that travelled roughly 3 billion years, Earth at the moment of departure would have been a younger planet entirely. The oceans were here. The atmosphere was here, though it was an atmosphere no human being could breathe, thin in oxygen, thick with gases that would be toxic to us now. Life existed, but it was microbial and scattered through those ancient seas in forms that left almost no trace. Single cells, chemistry experimenting with itself, no sound on land, no footprints anywhere, no structures, just water and rock and sky and the slow patient work of biology finding its footing. And the signal kept travelling. Hundreds of millions of years passed, then another 100 million. Life slowly grew more complex. The first organisms with multiple cells appeared, then the first creatures with bodies recognizable as bodies. The oceans filled with strange, soft life unlike anything alive today. Evolution was running its experiments in the dark, trying shapes and strategies with no audience and no particular destination, and the signal kept travelling. More hundreds of millions of years. Hard parts appeared shells, then bones. Then the scaffolding of creatures that could move with purpose and speed. Life crawled out of the ocean and onto land. Forests appeared for the first time in Earth's history, enormous and strange, filled with trees unlike anything growing today, releasing spores into an atmosphere that was slowly, incrementally filling with oxygen. Insects the size of your forearm flew through those forests. Amphibians moved between water and land. The planet was inhabited, thoroughly, by creatures that left no living descendants you would recognize. And the signal kept travelling. Then came the age most people picture when they think of prehistoric Earth. Dinosaurs emerged from earlier reptile lineages and spread across every continent, filling ecological roles that would look familiar in outline even if the animals themselves would not. They were fast, varied, and dominant in ways that lasted longer than anything in human history. For 160 million years, they were the signature creatures of this planet, and the signal kept travelling. 66 million years ago, a rock roughly the size of a small city came in from space at an angle and struck the shallow sea that covered what is now the Yucatan Peninsula. The impact released energy that is genuinely difficult to describe in human terms. The sky darkened. Temperatures swung wildly. Most large animals died within a geologically short time. The non-avian dinosaurs were gone. What survived was different, smaller, more adaptable. Mammals that had been living in the margins for tens of millions of years, mostly small and nocturnal, began diversifying into every ecological space the extinctions had vacated. Grasslands spread. Forests changed. The continents continued their slow drift into configurations you would recognize on a modern map, and the signal kept traveling. A few million years ago, on the African continent, something happened in a lineage of primates that had been evolving toward larger brains and more dexterous hands for a long time. They began walking upright with regularity. They began making tools. They began sharing information across generations in ways that accumulated, slowly, into something that would eventually be called culture. They spread out of Africa, across Asia, into Europe, eventually across land bridges into the Americas and out across the Pacific. And the signal kept travelling. 10,000 years ago, some of those humans began farming. Fixed settlements appeared, then cities, then writing. Astronomers in ancient Babylon tracked the movements of planets and developed mathematics to predict them. Observers in China recorded supernovae visible in daylight. Greek philosophers argued about whether the stars were fires or holes in a sphere. Arab astronomers named stars whose names we still use today. Copernicus proposed that Earth moved around the Sun. Galileo pointed a telescope at the night sky and found moons orbiting Jupiter. None of them could hear what was coming, and the signal kept travelling. In 1931, Karl Jansky accidentally discovered that our galaxy broadcasts in radio. In the decades that followed, engineers and astronomers built better and better instruments for listening to the sky. Parkes Observatory opened in 1961 in rural New South Wales. In 2001, on an ordinary night during an ordinary pulsar survey, the signal arrived. It touched the dish. It lasted a few milliseconds. It went into an archive file and was not recognized for 6 more years. The signal did not know any of this happened. It had no awareness of the journey. It simply moved, the way light moves, patient and indifferent and precise. It did not know about the asteroid or the dinosaurs or the first human being to look up at the sky with genuine curiosity about what was there. It did not know about the long chain of scientific work that eventually produced an instrument capable of detecting it. But we were here when it arrived, and that is not a small thing. There is a concept in astronomy called look-back time. When you observe a distant galaxy, you are not seeing it as it exists right now. You are seeing light that left it millions or billions of years ago. Every telescope is, in a sensor, a time machine. The farther it looks, the further back it sees. Fast radio bursts carry this quality to an almost uncomfortable extreme. When a signal from 3 billion light-years away reaches your telescope, you are receiving something that was sent before complex animals existed on this planet. The event that produced it happened in a universe that did not yet contain anything that would ever recognize it as significant. It crossed the universe during the entirety of complex life's existence on Earth, arrived after all of that, and for the first time in the history of its journey, something looked at it and asked what it was. A species that has existed for a tiny fraction of the signal's travel time, asking questions about where it came from. There is something in that worth holding for a moment. Before we move on, when you find something in the universe that should not exist, The first instinct is to check your instruments. The second instinct is to check them again. And the third, once you have exhausted every reasonable explanation involving faulty equipment or human error, is to sit down with a blank page and start asking what kind of physics could possibly produce something like this. That was exactly where astronomers found themselves in the years after the Lorimer burst was confirmed. The signal was real. The dispersion was real. The implied distance was real. And that meant the implied energy was real, which meant something out there in the universe was doing something that no existing model of astrophysics had predicted or prepared anyone for. The question was simple on the surface and deeply uncomfortable underneath. What makes a fast radio burst? The first thing any physicist does with an energetic event is look at the timescale. A very brief event means a very compact source. That constraint immediately ruled out entire categories of objects. Whole galaxies were out. Giant gas clouds were out. Anything extended or diffuse was out. You needed something small, something dense, something capable of releasing extraordinary energy in an extraordinarily short time without simply destroying itself in the process. The leading candidates were the dead remnants of massive stars, neutron stars, white dwarfs, black holes, objects that form when large stars exhaust their fuel and collapse under their own gravity into configurations that ordinary matter never reaches under normal conditions. Neutron star mergers were an early favourite. When two neutron stars orbit each other closely enough, they spiral inward over millions of years and eventually collide. The collision is violent beyond easy description. It releases enormous energy in a very short time. The math worked out reasonably well. The energy scale was right. The timescale was right. There was one problem. A merger destroys both neutron stars. It is a one-time event. Whatever forms from it is something new and different. The original objects are gone. If neutron star mergers produced fast radio bursts, every burst should happen exactly once. No source should ever fire twice. The gun fires and the gun ceases to exist. For a while, this seemed consistent with what was observed. Every fast radio burst detected in those early years appeared exactly once. No source fired twice. The merger model, and others like it, built around catastrophic one-time events, held up reasonably well against a limited data set. Other proposals circulated through the literature as well. Some researchers suggested that fast radio bursts might come from the final evaporation of small primordial black holes, a process predicted by Stephen Hawking's theoretical work on quantum effects near event horizons. Others proposed scenarios involving cosmic strings, hypothetical defects in the fabric of space-time left over from the earliest moments after the Big Bang. Others looked at highly magnetized neutron stars experiencing violent surface activity. Each model had strengths, and each had problems, and none commanded a clear majority of support. And then there was the question that surfaces whenever human beings encounter unexplained signals arriving from deep space. The question deserves a real answer rather than a dismissal. So here it is. When pulsars were first discovered in 1967 by a graduate student named Jocelyn Bell, the signals were so regular and so precise that the team nicknamed the first few sources LGM, which stood for Little Green Men, before the neutron star explanation emerged. They were joking, mostly, but the joke pointed at something real unexplained. Regularity in a signal from space triggers an instinctive response in human beings that has nothing to do with scientific training. Fast radio bursts triggered a version of that same response. The signals were strange enough, energetic enough, and mysterious enough that the possibility of an artificial origin came up in serious discussions as well as casual ones. Here is the honest position. Nobody can prove with absolute certainty that no fast radio burst has ever been produced by a technological civilization somewhere in the universe. That statement is true. But here is what is also true. The universe has spent 13.8 billion years demonstrating a remarkable capacity to produce violent, energetic, and deeply strange phenomena through entirely natural processes. Every time in the history of radio astronomy that an unexplained signal was considered as a possible sign of intelligence, The eventual explanation turned out to be a natural process we simply had not understood yet. Pulsars were the most dramatic example, but not the only one. The universe does not need intelligence to be strange. Physics, left to operate under extreme conditions, produces things that would seem impossible if you encountered them without knowing the physics behind them. Neutron stars spinning hundreds of times per second. Black holes bending space-time so severely that our equations need careful adjustment to remain accurate nearby. Magnetars with field strength so extreme that they alter the behavior of atoms. These things are not strange because something designed them to be. They are strange because the universe has no obligation to operate within the limits of human intuition. None of that resolved the central problem about fast radio bursts. Because in 2012, something happened that dismantled the leading theoretical frameworks almost overnight. A fast radio burst fired again. Not a new burst from a new source. The same source. The same position in the sky. A signal that had been detected once before was now detected again. And again. And again. All coming unmistakably from the same location. The source that would eventually be catalogued as FRB 121102 was repeating. Just like that. Every model built on the assumption of catastrophic one-time events collapsed. If the source was repeating, it had survived. Whatever was producing these bursts was not destroying itself in the process. It was there before the first burst. It was there after. And it was still there. Still firing. As if releasing all that energy was something it could simply do and then recover from. The merger models were wrong. At least for this source. The evaporating black hole models were wrong. Anything that required the source to be consumed in a single catastrophic event was wrong, because the source was plainly still intact and still active. The question that had seemed to be approaching an answer opened back up completely. Whatever makes a fast radio burst, at least in some cases, is not destroyed by making it. That constraint, added to everything already known about compactness and energy, began pointing towards something very specific, something that could survive its own violence, something small and dense and extraordinarily energetic that could repeat these bursts without tearing itself apart, something the universe, it turned out, had already built. It was a night like a lot of other nights at the telescope. The kind of night where the work is mostly waiting. Data comes in. The computers process it. The researchers check the outputs. And most of the time the outputs say nothing particularly interesting. That is how it goes in radio astronomy more often than not. You build the instruments. You point them at the sky. You wait. And you try not to let the long stretches of ordinary data make you careless about the moments that are not ordinary at all. In 2012, a team using the Arecibo Observatory in Puerto Rico detected a fast radio burst from a source that had already been seen before. Same coordinates, same general signal characteristics. The same place in the sky had fired twice. Nobody was certain what to make of it immediately. A single repeated detection could still be coincidence, could still be some artifact of the data pipeline, could still be something mundane, dressed up as something remarkable. Radio astronomy had taught everyone involved to be skeptical first. The microwave oven story was still fresh enough in collective memory to keep enthusiasm cautious. So they kept watching. The source fired again. And again. Each time, the team turned their instruments back to that same patch of sky and waited. Each time, after some interval they could not predict, the source produced another burst. Not identical bursts. The signals varied in intensity and in their internal structure, but they all came from the same position, and that position was not moving, and something there was clearly and repeatedly doing something. One burst felt like an accident. A repeating burst felt like a place. That shift sounds simple, but it restructured everything. Before the repeater, every fast radio burst was an event. Something that happened and was over. After the repeater, at least one burst was a location, a specific address in the universe where something was actively, persistently, doing this, And once you have an address, you can study it, you can watch it, you can send every instrument you have in its direction and wait for it to show you more. The source was eventually catalogued as FRB 121102. Teams at observatories around the world began pointing their instruments toward it whenever they could get time. The Arecibo telescope in Puerto Rico. At that point, the largest single-dish radio telescope on Earth, became the primary instrument for catching new bursts. Researchers stayed up through the night watching the data stream, waiting for the characteristic spike that meant it had fired again. Burst after burst came in over the following years. Dozens of them. Each one was slightly different from the last. But each one bore the marks of the same underlying source. The emission was not random noise. There was structure inside the bursts, patterns in how the frequencies evolved, hints of geometry and motion in the object producing them. What the team needed most was a precise location. Radio telescopes have limited angular resolution, meaning they can tell you roughly which part of the sky a signal comes from, but not with the pinpoint accuracy needed to identify a specific galaxy among the thousands that might lie along any given line of sight. To do that, you need either a very high-resolution instrument or a network of telescopes spread far apart, whose combined observations can be triangulated to a precise position. In 2017, using the Very Large Array in New Mexico and coordinating with several other telescopes, a team finally nailed it. The source was in a dwarf galaxy, a small, irregular galaxy about 3 billion light-years away, in the direction of the constellation Auriga. Not a large, elegant spiral like the Milky Way, not a massive elliptical, a compact, actively star-forming galaxy, the kind filled with young, massive stars and the energetic processes that accompany them. And within that galaxy, the burst source was associated with a persistent background of radio emission, a steady glow coming from the same region even between bursts, suggesting an environment that was not just active, but magnetically and energetically intense in a sustained way. 3 billion light-years. The signal had crossed that distance to reach us. In the time it was travelling, complex life was just beginning its first experiments on Earth. The source had been sitting in that dwarf galaxy, doing whatever it does, for longer than multicellular life has existed on this planet, and it was still going. What does an object look like that can do this? Releasing enormous amounts of energy repeatedly, without destroying itself, from a region compact enough to produce millisecond bursts, for a duration measured in at least hundreds of millions of years, if not longer. The theorists had a candidate. They had been arguing for it for years, and the properties of FRB 121102, its location in an active star-forming region, its persistent radio environment, its ability to repeat without apparent decline, fit that candidate better than anything else in the known universe. But confirming a theory requires more than a good fit. It requires catching the thing in the act, and that would take a few more years, and a source much closer to home. Meanwhile, as more observatories joined the search and instruments improved, other repeating sources began turning up. Not just one or two, dozens. Each new repeater confirmed that the first one was not an anomaly. Repetition was a real property of at least some fast radio burst sources, and the universe contained more examples of it than the original discovery had suggested. But here is where things grew more complicated rather than simpler. Not every fast radio burst repeated. Most sources, even after extensive follow-up observation, produced a single burst and nothing more, despite teams pointing their telescopes back at the same position for hours, days, sometimes months. No second burst appeared. These non-repeaters were real, numerous, and they seemed to behave differently from the repeaters in subtle ways. The burst structures were different. The environments, when known, were sometimes different. Were non-repeaters simply repeaters that happened not to fire during any observation window? Or were they a genuinely different class of object, something that could only produce one burst before going dark? The universe was not offering a simple answer. What it was offering was a better question. What kind of object survives its own impossible flashes? To understand what makes a fast radio burst, you first have to understand what a star leaves behind when it dies. Most stars die quietly. By cosmic standards, our Sun, in about 5 billion years, will exhaust the hydrogen in its core and expand into a red giant, swelling outward to swallow the inner planets before eventually shedding its outer layers into space. What remains at the centre will be a white dwarf, roughly the size of Earth but containing most of the Sun's mass, slowly cooling over billions of years into darkness. Gradual, undramatic, a long fade. Massive stars are different. When a star with 10 or 20 or more times the mass of our Sun reaches the end of its fuel supply, the collapse of its core happens not over millions of years but in less than a second. Gravity wins instantly and completely. The outer layers, still falling inward when the core suddenly stops collapsing, rebound off the rigid remnant and blast outward in a supernova explosion bright enough to outshine the entire galaxy containing it, visible across billions of light years. What happens to the core during that collapse is one of the most extreme transformations that matter undergoes anywhere in the observable universe. As the core falls inward, density climbs to levels that exist nowhere else under ordinary circumstances. Electrons and protons are forced together, merging into neutrons under pressure so intense that the quantum rules governing matter are pushed to their absolute limit. The collapse stops not because of any conventional force, but because of a quantum effect. Neutrons resist being packed into the same quantum state, and that resistance, at these densities, is enough to halt the infall. What stops the collapse is approximately 20 kilometers across. A neutron star, containing more mass than our Sun, compressed into a sphere smaller than a city. A single teaspoon of neutron star material would weigh hundreds of millions of tons on Earth. Not because it is chemically unusual, but because the space between particles that accounts for almost all the volume of ordinary matter has been essentially eliminated. Neutron stars also spin, because the original stellar core was rotating, and because angular momentum is conserved when it collapses from something the size of a large star into something the size of a city. That gentle rotation becomes something far faster. Some neutron stars spin hundreds of times per second. Their equators move at a significant fraction of the speed of light, and they have magnetic fields. Stars have magnetic fields generated by the movement of charged plasma in their interiors. When a star collapses into a neutron star, those field lines are compressed along with everything else. The same magnetic flux distributed across a star hundreds of thousands of kilometers wide gets squeezed into a sphere 20 kilometers wide. The field intensifies dramatically. For most neutron stars, the resulting magnetic field is already far beyond anything familiar from everyday experience. But some neutron stars end up with fields so extreme that they occupy a category entirely their own. These are magnetars. A magnetar is not large by cosmic standards. It is not dramatic to look at, not luminous like a young blue star, not expansive like a nebula. It is small, denser, and almost impossibly intense, as if the universe folded an entire storm into something the size of a city and then compressed that city until the space between atoms nearly vanished. To get a sense of the magnetic field strength, consider a few comparisons. A typical refrigerator magnet produces a field of roughly 0.01 Tesla. A hospital MRI machine runs at 1.5 to 3 Tesla. Strong enough to pull metal objects across a room with enough force to injure someone. Earth's own magnetic field, the one that makes compasses work and shields us from solar particles, is a fraction of a millitesla. A magnetar's field runs to roughly 100 quadrillion times Earth's. At that intensity, the magnetic field stops behaving the way fields behave in everyday experience and starts reshaping the physical environment around the star. Atoms near a magnetar become elongated along the field lines, stretched from their normal spherical shape into elongated forms by the overwhelming magnetic pressure. The vacuum itself, the empty space near the magnetar, behaves strangely in ways that only become relevant at field strengths like these. Light travelling close to a magnetar bends and splits in ways it simply does not elsewhere. In 2004, A magnetar in our own galaxy called SGR 1806-20 produced what astronomers classify as a giant flare. The burst of gamma rays and high-energy radiation it released in a fraction of a second was intense enough to measurably brighten Earth's ionosphere. The upper layer of our atmosphere, where incoming radiation ionizes the gas. The source was roughly 50,000 light-years away. From 50,000 light-years, a magnetar produced a burst powerful enough to affect Earth's upper atmosphere. Now, consider what such an object might do to the radio spectrum. The surface of a neutron star is not smooth or static. It has a crust, a layer of dense crystalline material, and that crust is under enormous stress from the magnetic field pushing and twisting through it from below. Occasionally, the accumulated stress exceeds the strength of the material, and the crust fractures in what astronomers call a starquake. When that happens, the magnetic field configuration changes suddenly. Enormous energy stored in the twisted field is released in a burst that can accelerate charged particles to extraordinary speeds. Those particles, streaming outward along field lines that are themselves shifting and reconfiguring, produce coherent radio emission, a synchronized burst of radio waves rather than the scattered random noise you would get from a thermal source. The brevity of the burst follows from the compactness of the star. The extraordinary energy follows from the extraordinary field strength. The coherence of the emission follows from the organized geometry of those field lines. Magnetars are built, in a sense, to do something very much like what fast radio bursts require. There is also a process called magnetic reconnection, where magnetic field lines of opposite polarity come close enough to break and reconnect in a different configuration, releasing stored magnetic energy in a sudden burst. This happens on the Sun during solar flares, producing eruptions powerful enough to disrupt satellite communications and power grids on Earth when directed our way. On a magnetar, the same process operates under field conditions billions of times more extreme. A magnetar experiencing a starquake or a large reconnection event has the compact size, the energy reserves, and the physical mechanism to produce a burst of coherent radio emission lasting milliseconds and releasing extraordinary amounts of energy. The theory was compelling, the physics was sound, but for years it remained theoretical. Nobody had directly watched a magnetar produce a fast radio burst. The connection was built on inference and calculation, not observation. That gap closed on April 28th, 2020, and when it closed in our own backyard. For years, every fast radio burst detected on Earth had one thing in common. It came from somewhere else, billions of light years away. Other galaxies, distant corners of the observable universe that no human spacecraft will ever reach, whose individual stars we will never resolve, whose properties we could only infer from the brief signals they sent across intergalactic space. The sources were real, but they were remote in a way that made detailed study nearly impossible. We could catch the bursts, we could measure their properties, but the objects producing them were far beyond any instrument capable of seeing them as individual things. Then, in the spring of 2020, something changed. A magnetar sitting roughly 30,000 light-years from Earth, well within our own Milky Way, in the same general neighborhood as many other objects we study routinely, produced something extraordinary. The source was not new or mysterious in its existence. It had been catalogued years earlier under the designation SGR 1935+2154. Astronomers knew it as an active magnetar, the kind that periodically produces X-ray and gamma-ray bursts as its stressed crust fractures and its magnetic field releases stored energy. It was a known object with a known character. What it produced in April of 2020 was different from anything it had done before. On the morning of April 28th, multiple radio telescopes on different continents detected a burst from SGR 1935+2154 that was unlike typical magnetar X-ray activity. It was a radio burst, brief, bright, and structured in ways that matched the properties of fast radio bursts detected from other galaxies. The CHIME telescope in Canada caught it, The Survey for Transient Astronomical Radio Emission in Canada caught it. A telescope in California caught it. Within hours, word was moving through the astronomical community that something significant had happened. This was the moment the theory became evidence. For the first time, astronomers had watched a magnetar, a specific known magnetar with a documented history, produce a burst of radio emission consistent with what fast radio bursts look like from billions of light years away. Think about what that means in practice. Every fast radio burst detected before this one had arrived from so far away that its source was invisible as an individual object. It was a signal from a place. The object producing it was inferred. The theory connecting magnetars to fast radio bursts was a best explanation built on circumstantial evidence. However good that evidence was, the April 28th burst was different. The source was known. It had been studied in X-rays and gamma rays for years. Its properties as a magnetar were documented, and when it produced a radio burst, the characteristics of that burst matched what the theory predicted a magnetar burst should look like. The mechanism that theorists had been proposing for years, stressed magnetic crust, sudden energy release, coherent radio emission from accelerated particles, produced exactly the kind of signal it was supposed to produce. Now, there is an important qualification that needs to stay in the picture. The burst from SGR 1935 plus 2154 was weaker than the typical extragalactic fast radio burst by a factor of roughly 1,000 or more. If you place this magnetar at the distance of the nearest known extragalactic repeater, its burst would have been completely undetectable with current instruments. The gap in energy between the galactic event and the most powerful extragalactic events is real and not trivial. This means either that magnetars can produce bursts across an enormous range of energies, with the galactic event sitting at the lower end of a distribution that extends much higher under different conditions, or that the most powerful extragalactic fast radio bursts require something additional that this particular magnetar did not provide. A younger magnetar, with a stronger field, a different configuration of surrounding material, a more extreme version of the same process. Or, as a growing number of researchers have suggested, there may be more than one type of object producing what we collectively call fast radio bursts. The galactic detection opened a door. It confirmed the chain of reasoning from compact remnant to starquake to coherent radio emission. It gave theorists a real event to model in detail at a distance where the source was known and well studied. It let radio astronomers compare notes with X-ray and gamma-ray astronomers who had been watching the same object from different angles. But it did not close the mystery. In the weeks before the April burst, SGR 1935 plus 2154 had produced an elevated rate of shorter X-ray bursts, a kind of seismic build-up in the magnetar crust, suggesting that stress was accumulating before the larger release. The radio burst came in the context of activity, not as an isolated random event. This was another data point about how magnetar bursts might work, how they might relate to cycles of stress and release in the crust. And then, within a few months, the magnetar went quiet again. Not permanently, just quiet, the way active systems sometimes go through periods of reduced activity before building back up. The telescope kept watching, the magnetar kept waiting, and somewhere else in the universe, in a dwarf galaxy, 3 billion light-years away in the direction of the constellation Auriga, FRB 121102 fired again, and again. The galactic burst had given researchers the confirmation that the mechanism was real. The extragalactic repeaters were telling them that the mechanism could sustain itself over enormous timescales in at least some object. The picture was becoming clearer, but it was also, at the same moment, becoming more complicated. The more we found, the less fast radio bursts looked like one thing. That sentence runs against how scientific mysteries are supposed to resolve. You begin with confusion. Data accumulates. The data points toward an explanation. The explanation holds up under scrutiny. The mystery closes. Everyone moves on to the next problem. Fast radio bursts did not follow that arc. Every new observation confirmed that magnetars were real players in the story. The galactic detection was solid. The theoretical framework was sound. And yet, the larger the catalogue grew, the more apparent it became that the category called fast radio bursts was not a single phenomenon waiting for a single explanation. It was a family, possibly a large and diverse one, with members that shared a superficial resemblance but came from genuinely different circumstances. Think about what happens when you walk into a dark forest at night and start hearing sounds. You hear something rustling in the undergrowth, then something calling from the canopy, then something moving through water nearby. You might initially call all of it simply animal noise, because that is the most useful category available to you in the dark. But as the night goes on and your ears adjust, you start realizing that what you called one thing is actually many things. Different creatures, different behaviors, different biology. You had been naming a family, not a species. Fast radio burst research arrived at a similar moment. The repeaters were the first complication, but the repeaters themselves turned out not to be a single uniform population. They varied from each other in ways that resisted simple explanation. FRB 180916 was one of the more unusual cases, detected by the CHIME telescope in Canada. It turned out to have an activity cycle. It did not fire randomly across time. It produced bursts for roughly 4 days out of every 16, then went quiet for the remaining 12, then active again, then quiet again, repeating the pattern with enough consistency that it was clearly real. A 16-day period. What imposes a 16-day period on a magnetar burst source? Several possibilities have been seriously proposed. The magnetar might be in a binary system, orbiting a companion star, whose wind or disk periodically obscures or interrupts the emission. The spin axis of the magnetar might be precessing, wobbling the way a spinning top does, sweeping the emission region in and out of the line of sight on a predictable cycle. The magnetar's internal magnetic activity might itself cycle on that timescale. None of these has been confirmed. All remain candidates. The original repeater, FRB 121102, had its own complications. Detailed measurements of its signals revealed an extremely magnetized environment along the line of sight. The radio waves arriving from it showed enormous Faraday rotation, a twisting of the wave's polarization that indicates very strong magnetic fields somewhere between the source and Earth, likely very close to the source itself. The environment around it was not just active in terms of burst production, it was magnetically extreme in a broader sense, suggesting either that the magnetar sat within a dense magnetized nebula, possibly the expanding remnant from its own birth supernova, or that something else nearby was contributing intense magnetic fields. Then there were the fast radio bursts that refused to fit the magnetar model comfortably at all. Some were localized to old elliptical galaxies where star formation had essentially ceased billions of years ago, galaxies where the young, highly magnetized, recently born neutron stars that theorists prefer as magnetar candidates should be rare or non-existent. You need massive stars to produce magnetars. You need star formation to produce massive stars. In a galaxy that stopped forming stars 2 billion years ago, the supply of young active magnetars should be running very thin. And yet, the bursts were there. Either some magnetars stay active for far longer than current models predict, which would require revising the theoretical understanding of how quickly these objects lose their magnetic energy, or the sources in old elliptical galaxies are something different entirely. A different class of compact remnant, a different physical process producing a signal that looks similar on the surface. The non-repeaters added their own puzzle. When researchers examined large samples carefully, they noticed that non-repeater bursts tended to look systematically different from repeater bursts, not just in whether they repeated, but in their shape. Non-repeater bursts tended to be smoother and more symmetric. Repeater bursts more often showed complex internal structure, with multiple subpulses drifting in frequency across the burst duration. If all fast radio bursts came from the same class of object doing the same thing, why would there be consistent differences in what the bursts looked like depending on whether the source repeated One possibility is simple observational bias. We call a source a non-repeater because we have not seen it fire twice. But any given telescope observes any particular patch of sky for only a small fraction of total time, a source that repeats infrequently, once every few years or decades, might fire during one observation window and not be caught firing again during any subsequent window. In that case, the non-repeater category might simply be the repeater category viewed from a disadvantageous observing schedule. But another possibility, taken seriously by a growing number of researchers, is that there are genuinely distinct populations, magnetars responsible for some other class of compact object responsible for others, and perhaps some fraction of non-repeaters coming from truly catastrophic one-time events of the kind that early theories proposed, where the source really is destroyed in the process and will never fire again. The universe rarely limits itself to one mechanism when multiple mechanisms are available and produce similar-looking results. A flash of visible light in everyday experience can come from a camera, a candle, a welding arc, a firefly, a lightning bolt, or a laser pointer. All produce something you might casually call a flash of light. All look broadly similar if you are not paying close attention, but they arise from completely different physical processes, involve completely different energetics, and behave in entirely different ways under examination. Grouping them all as flashes would not be wrong exactly, but it would obscure almost everything interesting about them. Fast radio bursts may be in exactly that position. What we observe, arriving at our telescopes as brief intense radio pulses from cosmological distances, is a category defined by how the signals appear to us: compact, energetic, brief, dispersed in ways that indicate extragalactic origin. But beneath that observational definition, there may be several genuinely distinct physical processes all producing signals that meet those criteria. Magnetars may account for most of them, or for the repeaters specifically, or for the ones found in young star-forming galaxies. We do not yet know. What we do know is that the mystery did not close when SGR 1935 plus 2154 fired its galactic burst in April of 2020. It opened further. The confirmation that magnetars can produce fast radio burst-like events was real and important, but it came with a set of remaining questions that have not been answered, some of which have barely been fully formulated yet. Magnetars gave us a door. The house behind it turned out to have more rooms than anyone expected, and it turned out that the bursts themselves, whatever their origins, were doing something remarkable on their way to us, something that had nothing to do with the mystery of their source, and everything to do with what they were crossing. At some point in the study of any mystery, there is a moment when the thing you are investigating turns out to be a tool, not just a puzzle to solve, not just a phenomenon to classify. A tool, something you can use to see other things that nothing else can show you. That moment arrived for fast radio bursts gradually, through observations that were originally aimed at the source question and kept producing unexpected answers about something else entirely. The something else was the space between galaxies. Most people, when they think about intergalactic space, picture emptiness, and by most standards it is empty. A cubic meter of the void between galaxy clusters contains, on average, roughly one atom. 1. A cubic meter of air at sea level contains about 25 million trillion atoms. Intergalactic space makes the best vacuum achievable in an Earth laboratory look like a crowded room. But one atom per cubic meter, spread across hundreds of millions of light years, adds up. And here is the problem that cosmologists have been wrestling with for decades before fast radio bursts came along. When physicists calculate how much ordinary matter the universe should contain, based on the physics of the Big Bang and what we can measure about the large-scale structure of the cosmos, they get a specific number. When they then add up all the ordinary matter they can actually observe, in stars, in galaxies, in the hot gas detected around galaxy clusters, they get a smaller number. The gap between those two numbers represents roughly half of all the ordinary matter the universe is supposed to contain. Not dark matter, not some exotic unknown substance. Plain ordinary atoms, the same kind that make up you and everything around you. For a long time, this was called the missing baryon problem. The matter was not thought to be truly missing. The leading hypothesis was that it existed as extremely hot, extremely dilute gas scattered through the enormous spaces between galaxy filaments, too thin to emit any radiation detectable by existing instruments, too spread out to absorb background light in ways that showed up clearly in observations. The matter was there. The thinking went. We just had no way to see it. Fast radio bursts provided a way. Every burst that crosses the intergalactic medium accumulates dispersion from the electrons it passes through. We have already talked about how dispersion measures the total column of plasma between source and telescope. The crucial realization was that for bursts coming from known distances, where the redshift of the host galaxy could be measured independently, the dispersion measure could be used to directly estimate how much ionized matter existed in the intergalactic space along that line of sight. In 2020, a team of astronomers collected a sample of fast radio bursts with well-measured distances and compared their dispersion measures against those distances. The relationship they found matched the theoretical predictions for how much ionized matter should exist in the intergalactic medium if the missing baryons were distributed there as the leading hypothesis suggested. The matter was not missing. It had been there all along, too thin to shine, too diffused to absorb, invisible to every instrument built before radio telescopes learned to catch millisecond bursts from billions of light years away, and a collection of signals, each lasting a few milliseconds, had found it simply by passing through it. A flash carrying billions of years of history had resolved a problem in cosmology that persisted for decades. But dispersion is not the only information fast radio bursts carry about their journey. When radio waves pass through a magnetized plasma, the direction of their polarization rotates. The amount of rotation depends on the strength of the magnetic field, the density of the electrons in the plasma, and the distance the waves traveled through it. This effect is called Faraday rotation. By measuring the Faraday rotation in a fast radio burst signal, astronomers can probe the magnetic fields in the environments the burst crossed, including the magnetic fields of the intergalactic medium itself. Those magnetic fields are extraordinarily difficult to measure any other way. They are too weak and too diffused to produce detectable radiation on their own, but a fast radio burst, passing through them over billions of light years, accumulates a Faraday rotation signal that shows up clearly when the burst arrives. Each burst is, in this sense, a long baseline measurement of the magnetic landscape it crossed. And then there is the cosmic web. On the larger scales, the distribution of matter in the universe is not smooth. Galaxies cluster together in enormous filaments, strands of matter stretching hundreds of millions of light years across, forming a network that cosmologists call the cosmic web. Between these filaments are vast voids, regions where matter is extremely sparse, some stretching 500 million light years across. Most of the ordinary matter in the universe lives in these filaments, in the diffuse gas that threads them, too thin to observe directly but present in quantities that account for the missing baryons. Fast radio bursts cross this structure on their way to us. A burst that travelled 3 billion light-years passed through multiple filaments and multiple voids. The dispersion it accumulated in a filament is different from the dispersion it accumulated in a void. The scattering of its signal differs between dense and sparse environments. By comparing the properties of many bursts crossing many different lines of sight, astronomers are beginning to build a map of the cosmic web that no other observational technique can provide. What makes this particularly striking is what it says about the nature of fast radio bursts as scientific instruments. They were not designed for this. Nobody built them to map intergalactic matter or probe cosmic magnetic fields. They were produced by violent processes in distant galaxies for reasons that had nothing to do with cosmological cartography. But in the act of crossing the universe, they became sensors. The universe wrote information about itself onto every signal passing through it. And once we learned to read that writing, every burst became a measurement. The universe built a probe and launched it in every direction. All we had to do was learn to read what it carried. Fast radio bursts are not just mysteries to solve. They are flashlights passing through the dark between galaxies, and everything the dark contains is briefly illuminated in the way they arrive. There is a thought experiment worth trying before we go any further. Imagine you were born without the ability to hear, not partially deaf, not with some residual sound perception, completely without auditory input from birth. Your entire experience of the world would come through sight, touch, smell, taste. You would develop a full and rich understanding of your environment through those channels. You would have no sense of anything missing, because you would have no reference point for what sound adds to a picture of the world. Now imagine that at some point in your life, a device is developed that translates acoustic information into a form your nervous system can process. You put it on, and suddenly you become aware that the world has been producing an entirely different kind of information all along. Information arriving through a channel that was present the whole time but completely inaccessible to you. Not more of what you already knew. Something qualitatively different. A new dimension of reality that had been there your entire life and that you had no idea existed. That is roughly the position humanity was in before radio astronomy. The universe had been producing radio waves since long before Earth formed. Those waves had been arriving at our planet continuously, passing through the atmosphere, through buildings, through human bodies, carrying information about objects and processes distributed across billions of light years, and for the entirety of human history up to the 1930s. We were completely unaware that any of this was happening. We had one sense for observing the universe, visible light, and we had built extraordinary instruments to extend that sense. Telescopes that could gather light from galaxies billions of light years away, but it was still the same sense, still the narrow band our eyes evolved to detect. Radio astronomy was not an extension of that sense. It was a new sense entirely, and every new sense reveals things the previous senses could not have imagined. The challenge with fast radio burst science specifically is that the signals are brief, faint, and arrive unpredictably from any direction in the sky. A traditional telescope that points at one region of sky at a time is poorly suited to catching events like these. If you are watching east when the burst comes from the west, you miss it. If you are observing a known source when an unknown one fires somewhere else, you miss it. By the time you hear about a burst detected somewhere else and point your telescope at that position, the burst is over and the sky looks like nothing happened. What fast radio burst science needed was not a deeper eye. It needed wider ears. In the Okanagan Valley of British Columbia, sitting among dry hills and orchards that go dark well before midnight, there is a facility that looks like nothing most people associate with a telescope. The Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, consists of 4 enormous cylindrical reflectors, each one 100 meters long and 20 meters wide, lying on their sides with their openings facing up. They look less like telescopes than like oversized skateboard half-pipes made of wire mesh and aluminum. There is no dish that rotates to follow objects across the sky. Nothing points or tracks. The structure simply sits on the ground, fixed, staring straight up. The design is deliberate. CHIME does not point at things. It listens to a large strip of sky simultaneously, continuously, all the time. As Earth rotates, different parts of the sky drift through that strip. Over the course of each day, a significant portion of the northern sky passes through CHIME's field of view. The telescope does not choose where to look. It simply listens to whatever happens to be overhead, without interruption, without preference. What CHIME produces is not images in any traditional sense. It produces a continuous torrent of radio data from across the sky. Thousands of channels of simultaneous observation, recording the radio sky with coverage and continuity that no previous instrument approached. The problem with this design is data volume. CHIME generates enormous amounts of raw information every second before any filtering is applied. No team of human researchers could examine it manually. There is simply too much of it, arriving too fast. For human eyes looking for the brief characteristic spikes of a fast radio burst, This is where the third part of the system comes in. Computers running purpose-built algorithms process Chime's data stream continuously in real time. They are looking for signals with the right properties, brief duration, broadband radio emission, the characteristic frequency sweep of dispersion, brightness that stands out against the background. When a candidate meets those criteria, it is flagged automatically, time-stamped, and set aside for human review. The researchers then evaluate whether a flagged event is a real astrophysical signal or one of the many varieties of radio frequency interference that human technology produces constantly. The partnership between instrument and algorithm is not a minor technical detail. It is the reason the field changed as quickly as it did once Chime came online. In its first year of full operation, Chime detected more fast radio bursts than all previous instruments combined across all previous years of searching. That was not because the universe suddenly started producing more fast radio bursts. We found more because we finally built ears that were the right shape for the sound. This pattern repeats throughout the history of astronomy. The instrument shapes the discovery. Galileo's telescope revealed moons around Jupiter and mountains on the moon because it extended what eyes could already do. Radio telescopes revealed pulsars and quasars and the cosmic microwave background because they opened an entirely different channel. Gravitational wave detectors revealed the collisions of black holes because they listened not to electromagnetic radiation at all, but to ripples in the fabric of space-time. Each new capability disclosed phenomena that all previous instruments were blind to, not because those phenomena were new, but because the physics of detection finally matched the physics of the signal. Fast radio bursts were there before Chime. They were crossing the sky above British Columbia before the facility was built, before Canada existed as a country, before any human being had ever stood in that valley. The signals were always arriving. The question was only whether anything on the ground was listening in a way that could catch them. And there is something in that worth sitting with for a moment. Because we tend to think of scientific discoveries as events, a moment when something new enters the world. But fast radio bursts did not enter the world when we detected them. They were already in the world, passing through it, carrying information that the universe had embedded in them on their way across billions of light years. The discovery was not the creation of something new. It was the moment our ability to perceive reality expanded enough to register something that had been there all along. Every new instrument is, in that sense, less an invention than a revelation, not a new thing added to the universe, a new piece of the universe finally becoming visible. And this naturally raises a question that the history of astronomy makes very hard to dismiss. If fast radio bursts were crossing the sky above us for billions of years before we had the ears to hear them, what else is passing through us right now that we are not yet equipped to notice? We started this story in the dark, a telescope listening in a quiet field, you settling into the stillness of your room, a signal somewhere between its source and its destination, crossing space that has no landmarks and no witnesses, carrying inside its frequency structure a record of everything it passed through since before complex life existed on this planet. We began there because that is where the story actually lives, not in the history of scientific papers or the specifications of radio receivers, in the fact of the thing itself, the almost unreasonable fact that signals born in violent magnetic catastrophes in distant galaxies can cross billions of light years of space and arrive. Brief and enormously informative, at dishes we built in valleys and deserts and mountain ranges and placed in the path of whatever the universe decides to send. So let us look back at how much the picture has changed since that first chapter. We started with the observation that human beings had spent thousands of years looking at the sky and seeing only what their eyes were built to see. Karl Jansky, troubleshooting interference in a telephone line in 1931, accidentally discovered that our galaxy broadcasts in radio. That accident opened a door that led, through decades of patient instrument building, to the night in 2001 when a signal arrived at Parkes Observatory, sat in an archive for 6 years, and then told us something no one had been prepared to hear. The universe was producing events of extraordinary violence and brevity in galaxies billions of light years away. It was releasing, in milliseconds, amounts of energy that our sun requires days to match. And those events were sending radio bursts across the observable universe that arrived at our telescopes carrying detailed records of everything they had crossed. We had been living under that sky our entire lives and had no idea. Follow what we now understand from that starting point to here. A millisecond of duration is not a limitation of the signal. It is a physical fingerprint pointing toward a source that must be extraordinarily compact. Operating at the extreme end of what the universe permits, the brevity was always a clue. It told us, before we knew anything else, that whatever was out there was nothing like anything in ordinary experience. The dispersion of the signal is not distortion. It is autobiography. Every fast radio burst carries inside its frequency spread a record of the plasma and magnetic fields it moved through on its journey. A signal from 3 billion light-years away crossed intergalactic medium, galaxy halos, the diffuse cosmic web, and delivered all of that information to our instruments without any engineering on our part. The existence of repeating sources is not a complication, it is a revelation. It tells us that whatever produces these bursts is not consumed in the production of them. Something survives its own violence. Magnetas. Dead stars wrapped in magnetic fields of almost incomprehensible intensity match that description better than anything else in the known universe. The galactic burst of April 2020 confirmed that the mechanism was real. The theory became observation, and the bursts themselves illuminate the invisible architecture of the universe as they cross it. The missing baryons, the ordinary matter that cosmological models predicted and telescopes could not find, turned out to be exactly where the dispersion measures of fast radio bursts said it should be. The cosmic web is becoming mappable through the accumulated properties of thousands of bursts crossing it in every direction. A phenomenon that was invisible to us until recently has become one of our primary tools for studying the universe on its largest scales. But the part of this story worth carrying into the rest of your night is not the science. The science is remarkable, and it is ongoing, and it will continue producing things that revise and expand what we think we understand. The part worth carrying is something quieter. Fast radio bursts were not discovered and then noticed. They were present all along and eventually perceived. There is a difference, and the difference matters. Gravitational waves have been rippling through Earth since long before humans existed. Every collision of massive objects anywhere in the universe sends distortions through space-time in all directions. And those distortions pass through our planet continuously. We detected them for the first time in September of 2015. When an instrument sensitive enough to measure a change in distance smaller than 1/10,000th, the diameter of a proton finally registered the signature of 2 black holes, merging more than 1 billion light-years away. The event itself happened more than 1 billion years ago. The wave had been crossing the universe the entire time. We were simply the first moment in the planet's history when something on the ground was listening carefully enough to feel it. Neutrinos from the nuclear reactions in our sun pass through you right now. Roughly 65 billion of them cross every square centimetre of your body every second. They pass through you, through the floor beneath you, through the planet itself, interacting with ordinary matter so rarely that most of them complete the entire transit without affecting anything. They were passing through every person who ever lived. Nobody knew until the 1950s that they existed at all. Fast radio bursts belong to this lineage. Every time humanity has developed a genuinely new way of observing the universe, reality has turned out to be richer than the previous way of looking revealed. Not incrementally richer, qualitatively richer. The radio universe was not a slight elaboration of the visible universe. It was a different universe, operating on the same stage, invisible to every instrument built before Jansky's antenna. The pattern has repeated consistently enough that it is probably reasonable to treat it as a feature of the universe rather than a coincidence. There are channels carrying information that we have not yet found. The next one, whatever it is, will arrive with the same structure as the ones before. Something present all along. An instrument finally capable of detection. A discovery that reveals not just a new object or event, but a new layer of reality that was always there. We cannot know what we are missing. That is what missing means. But we can know, from the history of what we have found, that there is almost certainly something there. The telescope in the quiet field, the one we introduced at the beginning of this story, is still running. Right now, somewhere, a radio telescope array is processing a continuous stream of data from the sky. The algorithms are running, the data is being filtered and flagged. Somewhere in that stream, in a file that no human being has yet opened, there may already be a record of a fast radio burst that arrived tonight while you were listening to this. A few milliseconds of frequency structure, swept from high to low by the plasma it crossed on its way here, and inside those few milliseconds, a record of everything the universe put in its path. The science inside one burst is not small, and the fact of one burst is not small either. Something happened in a distant galaxy, something violent and brief and magnetically extreme, and that event sent a pulse of radio energy across the observable universe, through environments that have no names because no one has mapped them in detail, through voids where the nearest galaxy was hundreds of millions of light years in any direction, through the outer edges of our local group, into the Milky Way, and finally to a dish in a valley or a desert that we built and pointed at the sky and told to listen. The universe was not silent when we could not hear it. It was broadcasting to an audience that had not yet built the ears. And now, in this small window of cosmic time, in this particular moment, in the long history of a species that has existed for an eye blink compared to the signals it is learning to detect, we are finally beginning to hear. Right now, while you are lying in the quiet of wherever you are, something is happening in a distant galaxy that you will never see. A magnetar, small and dense and wrapped in a magnetic field of almost unimaginable intensity, is going through a moment of stress release in its crust. Field lines are shifting. Energy stored for years or decades in twisted magnetic geometry is suddenly, in a fraction of a second, finding a way out. A pulse of radio energy expands outward from the source at the speed of light, into the interior of its host galaxy, through the galaxy's outer halo, into the intergalactic medium, into the long dark between everything. It will not stop. Hundreds of millions of years will pass. The signal will still be travelling. The continents of Earth will have moved. Species alive today will be gone. The night sky, seen from wherever life exists at that point, will look different from the sky, you know. And the signal will still be travelling. More time, more dark, or distance, until it arrives, at whatever is listening. The universe does not guarantee an audience. Most of what has ever been produced in the cosmos has crossed space without being detected by anything, and will continue to do so. The rarity is not the signal. The signal is everywhere. Always. The rarity is the instrument. And behind the instrument, the patience to build it. And behind the patience, the curiosity that made building it feel worth doing. But sometimes the signal arrives when something is listening. And at that moment, the universe does something it could not do alone. It becomes known. You are lying somewhere quiet right now, and the sky above you is full of signals your body cannot register. Radio waves from distant galaxies are passing through the walls of your room. Gravitational waves from ancient mergers are moving through the floor. Neutrinos from the sun are crossing through you in numbers that would be astonishing if you could feel them. You cannot feel any of it. But somewhere, instruments can. And somewhere, a signal that began its journey longer ago than you can hold in your mind is still crossing the dark. Still patient. Still moving.